Okay, obviously, next up would be momentum budget after we do the temperature and salinity budgets, and the momentum budget is very closely linked to the salinity and heat budget because the mixed layer depth is determined by the density, and the mixed layer depth is closely related to the momentum, penetration, and advection terms. So currents are generated by momentum, and currents advect around the temperature and salinity, so they're all intimately linked together. So here is a blueprint illustrating the connections between the ocean's heat, salt, and momentum budgets. So these are the thin lines here. And highlighting the fact that the pathways for ocean-atmosphere interactions, which are these heavy lines, are mediated by these three budgets. Examples of atmospheric variables listed include air temperature, specific humidity, cloud cover, precipitation, and three-dimensional velocity vectors. So you have atmospheric air temperature, air humidity, clouds, precipitation, and winds, which interact at the surface with the ocean through heat budget and salt budget that we talked about. So ocean gives some energy back to the atmosphere, especially through evaporation, and it supplies mass through evaporation as well, and of course receives some back through precipitation. And the atmosphere provides momentum budget to the ocean, and as we said before, the ocean is largely forced from the top, so including the heating and cooling. The geothermal heating and other forcings interior to the ocean are not that significant compared to the forcing at the top, right? So write our Newton's law of motion, second law, F equals ma. So dV dt per unit mass is what you typically look at for ocean and atmosphere, because you are thinking about parcels of air or water moving around, and that should be equal to the sum of all forces. And you can split that vector into x, y, and z coordinates, writing du dt equals sum of fx, dv dt is sum of fy, and dw dt is sum of fz. And du dt here is the Lagrangian derivative, total derivative, material derivative, so it's partial u partial t plus the advection term u dot grad v, so u du dx plus v du dy plus w du dz, and so on for each direction. So these are the momentum or acceleration equations for zonal, meridional, and vertical directions. So we can split that material derivative into du dt. So partial terms du dt, dv dt, and dw dt equal the sum of all the forcings minus, so we moved the advection term to this side, so it's minus v dot grad u, and again divergence u here. This is the continuity equation. So when we do just the equations of motion for physical oceanography, we have 5 unknowns: u, v, w, temperature, and salinity. Knowing temperature and salinity, we can compute density using the relation. So we need 5 equations. So obviously there will be the thermodynamic equation for density as well. So we have heat budget equation, salinity budget equation, and the 3 momentum equations, right? So that gives us a complete set of equations. The continuity equation itself is for an incompressible fluid. So we can actually write, just like salinity budget and temperature budget, we can write a density budget equation, and assuming density rho is incompressible, which is very valid for the ocean, even though pressure effects are not that insignificant when you go deeper in the oceans, but in general That gives us the non-divergence equation in three-dimensional. So divergence v du dx plus dv dy plus dw dz becomes equal to 0 as the continuity equation. Okay, so what are the forces acting in the vertical? Of course, we have gravity. So schematic diagram illustrating role of gravity in deriving horizontal fluid accelerations by the way of pressure gradient force. So you have typically horizontal density and pressure gradients. So let's say area A1 and some height h, let's say a layer thickness between two levels, and you have mass m1 on one side, mass m2 on the other side. So pressure will be p1 and p2. For simplicity, assume that p1 is greater than p2, and gravity is always acting downward, although on a sphere you have to be careful because the gravity is towards the center of the earth. But when we look at a XYZ piece of the ocean, you have to remember that we are on a sphere, so there are some details there that matter when you actually want to do the full equations, which we're not getting into here. Okay, so if you just had pressure gradients driving the fluid flow in the ocean, then acceleration term could be just related to pressure gradient in x, pressure gradient in y, and vertical acceleration. Probably many of you have been exposed to the idea of the Earth being a very large sphere with a large radius, especially compared to the depth of the ocean. Since we are focused on the ocean, let's just think about the ocean depth, which is typically order 3 or 4 kilometers. Some places much deeper, some places shallower. So the ocean can be considered as a thin shell on a large sphere. So the horizontal motions tend to be much larger in magnitude than the vertical motions. So in the vertical, typically you end up balancing the gravitational force to the vertical pressure gradient force, and you end up with the so-called hydrostatic balance, which means at any level pressure is just equal to the weight of the fluid above, in which case it will be the ocean plus the atmosphere above, so atmospheric pressure at the surface plus the pressure due to the weight of the water. So in general the dw dt term is 0 in the ocean, even though in convective plumes where deep waters form, water can be sinking fast and W can be significant, but similarly in the atmosphere, convection is where W can be significant. But when you look at larger scales, the ocean is almost always in hydrostatic balance, and we will see that equation in a minute. To do the momentum balance, momentum budget, we will also need Coriolis effect, which is fairly straightforward. I have a separate podcast on YouTube you can look up, or in the other courses. Here we have also done it in the earlier part in the same course. So the effect of Coriolis can be simply thought of in terms of the rotation rate of the Earth. So because circumference is large here and you are rotating once in 24 hours, anything here has to be moving much faster than here. So if you start something in this direction and move towards lower latitudes, you will be carrying the Earth's east-west velocity here, which is much smaller than here. So as you move south, you will be falling behind because this Earth is moving faster. So you see that if you start here, these points move forward and you will fall behind, so you will be deflected to the right of the direction of motion. So going southward, you will be pushed west. Similarly, if you go north, you will be pushed to the east. So in the northern hemisphere, you are pushed to the right of the direction of motion, and in the southern hemisphere the Coriolis changes because you look from the bottom towards the South Pole, and you'll be pushed to the left of the direction of motion. We can think of it in terms of the centrifugal force we experience because we are on a rotating framework. So centrifugal force is given by mv squared over r, where v is the azimuthal velocity with which you are moving, so the longitudinal velocity, and r is the distance from the axis of rotation. Obviously that is on the surface because we are considering the ocean. So assuming f is maintained, we can write this as r, the distance, equal to mv squared over f, which means if v increases and f is the same and mass is the same for a parcel we are considering, then r has to increase. So you can think of it in many ways. So if you are moving, let's say, east to west, and the Earth is moving west to east as well, then if you are moving in the easterly direction, sorry, I should be careful, easterly can mean something else in meteorology. So if you are moving west to east, you are moving faster than the Earth, so v is increasing, which means r has to decrease, so you will be deflected towards the south again. And similarly, if you are moving from east to west, then v is decreasing, so r has to decrease, so you will go towards the north, so you will be deflected to the right again. So it's easier to understand the eastward and westward deflection when you're moving north or south, but when you're moving east or west, you can use this relation to see how your speed changes with respect to Earth, and why that should change your r, assuming f is almost the same. Okay, so that's the way to understand Coriolis effect on Earth. But for this introductory course, the best thing is to remember that in the northern hemisphere, no matter which direction you move, you will be deflected to the right of the direction of motion, and by the same token in the southern hemisphere, where things reverse, you will be deflected to this left of the direction of motion because of Coriolis. Coriolis only changes direction, it doesn't change the speed itself, so it's often referred to as the apparent force, but typically we just say Coriolis force without always saying Coriolis effect. We need to say Coriolis effect if we want to convey that it's an apparent force, but let's not worry about it and just call it Coriolis force. Okay, so we have approximately got our equations of motion and Coriolis. Now we will try to put these together and see how the various balances happen in the ocean, and what kind of motions they generate, and how that affects the momentum budget. Okay.